So with that, hello and welcome to the second in the series. And I think I'll just hand it over to James.
Good morning, everyone. So for today's open source drilling community meeting on Monday, March 21st, this is the second in the series of technical sessions. And today's presenter is Darlington Etaje, who's going to be presenting basically a model or methodology for implementing soft string and stiff string models for torque and drag calculations. So I'll hand it over to Darlington at this moment.
Thank you so much, James, and I'll just share my screen here. Right. Good morning, everyone. Thank you so much for being here. I appreciate the time, and I take it as a privilege to present to you this morning. My name is Darlington Etaje. I'm a PhD candidate at the U of C, and of course, my supervisor is Professor Roman Shaw, and I appreciate his effort to get me to this point. Thank you, James, for the introduction. So today I'll be looking at the concept of torque and drag, torque, drag, more concepts. I would try to show you why we need torque and drag analysis, the input and output data for torque and drag, look at a bit about the history. I won't waste time there. I'll go into the methods of calculating torque and drag, comparing soft string and stiff string models, the calculations, merits, demerits, and the Fstiff using finite element analysis. You really want to see that. And so at some point, I would be showing you just one page. One of the slides would be an important code to implement the soft string. And then another important code in terms of finite element method. So the concept basically is the fact that when you turn the drawstring at the surface, obviously the RPM will turn along with it. That torque causes the turning. Excuse me, but as you're drilling through the ground, there are torque losses due to friction, and eventually your side torque, which is reaction to deformation, which is what you need to break through to drill ahead, is in the opposite direction. So the idea of torque, of drag, is basically as you're trying to pull up an inclined surface, there's a force trying to pull the material, the mass, in the opposite direction. So it's that drag that we are calculating when it comes to torque and drag. And so torque is the power loss due to friction as you're transferring that surface bit to surface torque to the bit. And as you can see here, you're trying to turn in a particular direction, and then for you to go in that direction, you have to overcome that force, which is the torque that we're calculating. And drag is the difference between the static and tripping weight of the drawstring. So basically, I'm rotating here, and I'm rotating due to the surface torque that I've created. And then I have the downhole torque in the opposite direction based on friction. This contact force can be referred to as normal force. And obviously, because I'm pulling the drawstring at the surface, there's tension and compression happening. The weight obviously is acting downwards, the weight of the drawstring. So more concepts, the general idea is that while you're sliding, your torque is low and your drag is high, which is obvious because if you're dragging it through the hole, then so many things could be holding the drawstring behind. And then while you're rotating, you free up all that drag, and then your torque is high because that's when the formation is resisting the ability to turn. And so why do we need torque and drag? We need to minimize torque and drag forces while we're doing our trajectory design, determining hole condition to detect if problems are arising. You know, you design your drill string to reduce torque and drag, monitoring hole cleaning in real time. So all these things are what you need, but in more practical sense, if you have your buckling limit and your tensile limit, then obviously you want to be within the safe window when you're tripping out and tripping in. But if you don't stay in that safe window and you maybe make some changes in your friction factor wrongly, then you're going to buckle at some point, or you're going to have some kind of tension of your drawstring if you're going above the tensile limit. So that's why we really need the torque and drag to ensure that we stay within that safe window. So the inputs into torque and drag calculations will be the well path data, drawstring dimensions, drilling operations data, and hole conditions, while the output is the hook load, surface torque. The important plots that will make a lot of sense for everyone would be measured depth versus hook load, measured depth versus surface torque plot, and the frictional calibration. So in terms of history, so that guy. So Johansic was the first person to propose a soft string model, but of course ignores the bending stress of the drawstring. And then so many people have tried over time to improve that model and add some more spice and more conditions to what is possible downhole. And Mitchell in 2008 offered improvements to the classical soft string model by replacing the commonly used minimum curvature interpolation with a spline model. I haven't had time to read that in detail, but it's interesting to note this is not the entire history. There's still so many papers that have been done, even by people on this call over time. And so let's compare soft string and stiff string model. I deliberately did not name any of this so that we can really get to understand it. So there's a model here where you are modeling the drawstring according to the whole movement, almost as if it's a spaghetti on inside the hole and it's exactly fitting the directions of the hole. While this other one, you have some certain contact points where the drawstring is touching the hole, and that's where you're looking at your normal forces. In this case, your normal forces can be on any of these points in the hole. And so this one where there's some points in the hole where the drawstring is touching the hole, that's the stiff string consideration. And then the soft string is where the entire drawstring is touching the hole. So soft string modeling, stiff string modeling, there's no bending stiffness like you saw in the previous slide, and has a continuous contact with the wellbore. So just trying to make sure that concept is well understood. And the source of this paper, interestingly, is also the reason why we're here. This open source models paper by my supervisor and the other team. And then the stiff string modeling has bending stiffness, but considers bending stiffness and has point contact with the wellbore, right? So very important. So analytical modeling, it's all that soft string models. But for finite elements, finite modeling is a stiff string model where you can either use finite differences, finite elements, or semi-analytical techniques. Although my supervisor says you can still do all of this in soft string. I didn't see it in my research, so I just stayed with that. So generally called stiff string, all that different models, instead of just taking the whole drawstring and taking some formulas, calculating torque and drag, soft string. But if you're going to break it down into different nodes, then you're looking at stiff string modeling. And so, so in terms of further comparison, it can be used for real-time torque and drag monitoring because of short time required for its application. Yeah, it's very straightforward. I actually have experienced that stiff string will take a long time in coding on MATLAB, because as the nodes are increasing, the variables, the matrices are expanding, and then it becomes really difficult to get such results as quickly as you need. But both of them will show similar results in a smooth wellbore geometry. but they give different predictions in the tortuous well. But obviously that this stiff string, I feel, will be more accurate in the tortuous wellbore, because it's not all the points of the drawstring that will be touching the wellbore. So soft string modeling from first principles. So the structure of this modeling is you have to first consider when there's no dogleg and you have horizontal or inclined. And then either when you have no motion or motion with friction or no friction, and then lowering if you're having with friction, which means you're moving, you're either lowering or raising the drawstring in terms of just that the whole pull and slack. So pull is lowering, slack is raising. And so with dogleg, you're either dropping or building, no friction with friction, no friction with friction, and both cases of friction, you're either lowering or raising, or that's pulling or lowering the drawstring. Now, when you're lowering, you could be also drilling, right? The only condition that is not considered here is something I'll show you in a few minutes. So the basic torque formula is the normal force times the frictional factor and times radius. And so because we're going bottom up, so you calculate first the bottom torque, and then you add it to the change of torque to get the torque at the top, basically. And that's the formula for the normal force. And the same thing goes here. You calculate the bottom force, add it to the tension change, and you get the force at the top. So drag, you calculate the drag by, and I will show you the breakdown. I just want to give you the summary first, and then we take it from scratch. Normal force multiplied by the friction factor. So the hook load for pulling would be that static hook load plus the drag. And then on the other hand, for slack is static hook load minus the drag. And so let's take it from that structure that I explained to you earlier, no motion, where it's just the normal force and the weight. So everything is equal, nothing is happening. More or less symmetrical with just having your drawstring in a horizontal plane. You're not drilling at that point. This is what is happening. Now, as soon as you start sliding, then your velocity is greater than 0. Depending on the direction that you're going. In this case, let's assume you're going left. That means your frictional force will go in the opposite direction. But it's still, nothing has gone wrong here. The frictional force is obviously the friction factor multiplied by the normal force. And then now you go on an inclined wellbore, where, as usual, you're calculating bottom, top. So you calculate your tension at the bottom, add the change in tension to get the tension at the top. But now you have friction because you're sliding. Now, depending on where you're going, so if you're lowering, if you're lowering your drawstring, obviously your friction force is going in the opposite direction. And if you're raising it, your friction force is going in that direction. And when you're lowering it, the important thing is that change in tension is that you're going to be subtracting the frictional force when you're lowering. And then if you are raising, you are adding that frictional force in order to calculate the change in tension. And then effect of doglegs, obviously, if you're dropping, meaning that you are reducing your inclination as you're drilling. Same thing, it's just now you have a change in direction. And the change in direction is the dogleg angle, which the azimuth and the inclination would account for. So if you are neglecting pipe rotation, then this would be the equation for your normal force. And then the tension is still doing a bit of calculation there, you get your tension force there. the change in tension, then including the impact of friction while dropping, while the pipe is rotating. The tension is still the same. But as you're lowering, you are, of course, as usual, subtracting that friction force, which is the mu n, and then you get the formula that you so require. And as usual, the torque is the mu times the normal force times the radius, which is diameter over 2. And the normal force, you just include the normal force equation, and that's what you get for the torque. So build up like all the different conditions. You either have a drop or you're having a build up in the well. And if you're building up, same conditions apply with rotating and neglecting friction and including friction. Same conditions apply to calculate your change in tension. So while lowering the pipe, again, as usual, you subtract the frictional force and the dogleg, considering the inclination change and the azimuth change. So I think the important code that I want to just specify is this code, which would show you how to calculate that top tension. I think you start from the bottom, calculating the bottom, which is the bottom force is the previous top force. So you have several components now. So the bottom force, it would be the previous top force. And then you, from that bottom force, you would, bottom tension, you calculate the pool the normal force for pool, changing tension, and then add the change to the bottom tension, and you get the top tension. So I just wanted to state that out there. Now, all the scenarios in 2D directions, you are either building only where your inclination, yes, your second inclination point is higher than the initial one. You're dropping only where your first inclination is greater than the second one. And then no build, no turn is when you have equal inclination and equal azimuth. So the other thing that I wanted to mention that wasn't there is the fact that you can turn. So it's not just building and dropping, you can turn. And whilst you're turning, of course, the azimuth is different if you build, the second inclination is greater than the first one. So all of these are all considered in those equations that we just walked through. The drop and turn, same thing, the azimuths are different. The first inclination is greater than the next one. And turn only where it's just the azimuth that's different. So the merits and demerits of soft string modeling is pretty much the industry standard, but those radial clearances are not considered, and it's neglecting bending stiffness. But obviously, those algorithms I just showed you now are very simple to code and put in and run. So it's simpler and easier to use with a basic laptop computer. It's just sufficient for, especially for those smooth geometry. This is sufficient to use. And then for the stiff string models, now we're looking at those forces across the different nodes in the drill string. And so the important thing to note is the introduction of the stiff force, which is the additional normal force due to pipe's stiffness in the bend. And it's this stiff force that I would be running you through the finite element analysis to calculate. But so of course, I just showed you one type of soft string modeling. There are several types of soft string modeling, but the addition to the whole situation is the stiff force, which is added to the bottom force of when you're doing that addition. So that wasn't included before in the soft string modeling. And basically, the equations will now be including that stiff force as you consider that rotational motion only or combine axial motion and rotation motion. And the equations obviously are different for straight pipe and for curved sections. But the biggest addition to the soft string model is the stiff force. And so the units. So the merits of the stiff string modeling is it provides more accurate analysis than the soft string models. But obviously it's more complex and takes time to compute. And that would be a problem because if you can't get the solution readily as you need it, then it's an issue because as the more components you're adding to the drill string, the more difficult it is to achieve. So calculating that stiff force using finite element method. So the focus is not to solve the problem, it's to make the problem solvable using computer methods. And you can either be doing flexibility method or the stiffness method. So the one I'm familiar with is the stiffness method, where what you're trying to calculate is the rotational and translational displacements. So the assumptions is that there is a linear relationship between the applied load and the displacement. And of course, the material will be Hooke's load. Equations of equilibrium shall be developed using the geometry of the wellbore. So the problem is that the kinematic indeterminacy is the number of joints with respect to axes that required to describe the response of the system to an arbitrary load. And then, so the model formulation is to convert that kinematic indeterminacy into a kinematic determinate structure. So the sign conventions are anti-clockwise end moment is positive. So basically your moments and rotations anti-clockwise are positive, your direction right is positive as well, upward is positive. And then on a 2D modeling, you'd have, if this is a pipe, or you can call it one component of the drill string, but this is 2D now. So usually the x-axis will go along the axis of the member meaning the components, and then the y-axis is perpendicular. So origin is at the G8 end, and your labeling is from left to right, and you mark rotations, then translations. So if I'm going to do that, then there's a rotation in this, I can call it P, and rotation in, so I mark the G8 end and then the K8 end, and also the upward force, upward displacement from, so these are the only two rotational conditions for 2D, and then upward force or upward displacement from G8 end to K8 end, and then axial displacement from G8 end to K8 end. So, but of course, what we are more interested in is the 3D modeling. And so you have Y, X, Z. So obviously they are all perpendicular to each other. So you have your rotational moments, which is what we're really interested in. And then the vector for rotation translation. So let's label this 3D member. So reference axis system, as usual. So I'll do this first, and then I'll show you the drill string. So basically, like I said, labeling from left to right, first mark rotation, then translation. So G8 end and K8 end. So obviously, as I said before, the x-axis goes in the direction, in the axial direction of the member, and that's the reason why you have it this way. And then you mark your rotations first. So you're marking, I'm just calling it L, the rotation at the G8 end for axial. So X, Y, Z, basically. Rotation at the K8 end, and then Y. So there are rotations in each direction. So each axis. And then after I finish the rotations, I go into the displacements for, you can see I'm going from left to right. So for Y, delta T, delta U, then Z, just like that. And so the rules of reactions in the 3D is translation in one end of x-axis causes translation on the other end. And consequently, but in the translation in y-axis causes rotation in the z-axis, and translation in the z-axis causes rotation in the y-axis. And rotation in one x-axis will cause, so rotation for x-axis, translation leads to translation on both sides from the g-ed end to the k-ed end. And then for translation for y and z, so y translation leads to z rotation, z translation leads to y rotation, and vice versa. And so the stiffness coefficient is k, so that I is the member, because there's, so each component that you, depending on how you want to break the third string, each component is a member, and so this is the impact location, and this is the reaction location. So just taking you back there. So all that labeling is what you're getting from. So if I'm rotating here at this end, then the impact location is, which this is y, so it will be the z of this guy. So that's just what I'm explaining. So, so like I said, a rotation here will cause a translation in the y-axis of the k-ed end. And so forces cause those displacements and moments cause a rotation. So basically, with the moments, you can be able to estimate your drag. With the forces, you can calculate that stiffness force that I was showing you in the stiff string. And so the stiffness matrix for a 3D member, like I said, it forces. So for the g-ed end, you have, which is the beginning side, you have forces and moments, and the k-ed end forces and moments, and all this labeling just the way we labeled it earlier. And so, and then each of those forces will lead to translation, and the moments will lead to rotation, just like that. So, like I said earlier, if you translate in the, if you create that force in the x-axis of the g-ed end, then you have a corresponding x-axis translation, and every other reaction is 0. If you create a translation in the y-axis, then you would have a rotation in the z-axis, which would have an equal rotation in the j-axis. But if you have a rotation in the j-axis, it leads to translation in the y-axis of the k-ed end, and every other thing is 0. And so just showing you how that stiffness matrix for 3D is calculated. So obviously translation in the z-axis will lead to rotation in the y-axis, and that will have an equal rotation in the y-axis in the g-ed end. But of course, with the g-ed end y-axis rotation, then you should have translation in the z-axis, and then every other reaction is 0. Same story, x-axis, everything else is 0. Y-axis, z-axis, another z for translation, which will also lead to rotational y-axis, and every other thing is 0. So the same concept continues across board. So let's look at this translation in the k-axis would, for y, in the y-axis in the k-ed end would lead to rotation in the z-axis in the g-ed end, and that will have an equal rotation in the z-axis of the k-ed end, and leading to translation in the y-axis of g-ed end, and every other thing is 0. So that concept continues across board, and that's how you have that stiffness matrix computed, basically. So this is symmetrical across, so you see across this, everything that you have here is just flipped over on the other side. So that's where you get this equation for the stiffness matrix. So coming now, how do we relate this to the drawstring model? You already understand that this is the northern, eastern, and TVD of the drawstring. So obviously the pipe is going into the ground in some direction that has a coordinates. The coordinates you can determine using the azimuth and the inclination, right? So with that being said, you understand that the drawstring axial path is true here, or so that's the reason why your x-axis is downward, and then you can fix anywhere to be your y and your z. So in order to get this further, you're going to break the drawstring into different members. So this is member 1, member 2, member 3, up onto member 9. And if you pick one of those members, basically the same thing. You're having, starting from rotation, this is your G-th end, your K-th end. And so you're having rotation in the x-axis, and then rotation in the y and z, just like that. So to calculate that first stiff, you determine the number of members, you calculate the moment of inertia and area. Moment of inertia is just 1/64 times the OD raised to the power 4 minus ID raised to the power 4, and then the area. And then you're calculating using your Young modulus, so multiply the moment of inertia, calculating torsional constant and actual rigidity. So, and then you calculate your transformation matrix. You obtain the length of each member. So depending on how you separate the nodes, it could be the recommended to be at some point within the pipe or the different components, but the length is needed for each member, and then obtain the number of joints, which is just the number of members plus 1. You calculate the transformation matrix in 3D space. So this 0 is a 3x3 matrix because the direction cosine is a 3x3 matrix, which is after lots of research. This is the formula for that. And then you calculate the number of restrained and unrestrained degree of freedom. So each reaction is 1 degree of freedom. So you calculate the number of restrained and unrestrained degree of freedom, calculate the global label of restrained degree of freedom. And then, so pretty much the moving parts are the unrestrained degree of freedom, determining the global label of members. So I'm just showing you exactly how put it in code and on MATLAB, and then determine the joint load vector and extract the load vector for the unrestrained degree of freedom. So in terms of restraint, where you have your stabilizers point of restraint. So I wanted to explain this further, but because of time, I'm not able to do that. And then from there, you determine your stiffness matrix, which is what I showed you in the previous slide. And then you calculate the stiffness coefficient of each member. And that way you will now get to determine your forces and moments. So those forces are the stiffness forces, which you now put in that addition to soft string model to develop the stiff string model calculations. And when you do those calculations, obviously, this matrix here gets bigger as you add more members. And as you add more members, is several of them, can get up to a billion matrices there. And so in terms of the other important code that I want to show is the transformation matrix. After you've done the direction cosine, is this bulk dial that allows you to achieve to achieve this structure in the transformation matrix, which you would now use in calculating the forces and moments. So for future work, obviously those assumptions in the soft string model should be improved on and accommodate all shortcomings. What I am thinking of doing is to see how I have a switch from soft string model to stiff string model. So if it's a smooth curve, then I'm using soft string model, but as the totality increases, I'm switching to stiff string model. That code I'm still working on. So thank you so much for listening. That's my presentation.
Very good. Thank you, Darlington. I have one question. I know there's lots of them that are going to show up, but in terms of post-buckling behavior, if you go to the stiff string model, do you account for the, I'll call it the change in axial stiffness as I buckle inside of a hole? So I've got a constrained buckling. You know, I'll go into helical buckling. In real life, it is constrained to be some kind of a wavelength. I didn't see where that would actually account for that deformation to spiral, or if you will, inside of the hole. Helical would be a helical path inside the hole.
Yeah, I think the finite element analysis takes care of that. But one way to critically address that is making sure that you're not just placing your nodes at the connections. You're placing nodes at the middle of a particular drill string. But I would answer that better later. I will look into that.
Okay, all right. By the way, I'm being real selfish. I have a very particular reason to do that. I've got a well that I believe helical buckling was part of a failure that we had recently, and it reduced the stiffness of the drill pipe, which meant that our tag bottom procedure was off. And anyway, so this is just a question about a very particular issue, but it probably occurs often when we don't think about it. So.
Hey, Darlington. Yeah, thanks again for that presentation. Just a couple of questions. Just in comparing the soft string and the stiff string, is there kind of any tendency for one method or the other to kind of overestimate or underestimate kind of the forces acting on the drill string, like, and kind of what goes into that?
Yes, so I think the one that would most likely underestimate will be the soft string model, right? Because obviously you are assuming the whole drill string is in connection to the. I think you are assuming the whole drill string is in connection with the wellbore. So yeah, that would. So in both cases, depending on what method you are using, you have potential to overestimate or underestimate. So I think the easiest way to make sure you're doing it right is to compare your result with what you're getting in the softwares that are approved out there.
Okay, thanks. Just one question on another kind of piece. So you mentioned kind of one of the pitfalls of the kind of stiff string and the finite element analysis is the kind of the computational complexity of the problem. Part of that is I think it's setting up or identifying kind of number of elements and setting up the mesh and you know, arranging the grid, right? Do you kind of have any guidelines on, you know, say you have like a drill string that's, I don't know, 15,000 feet or so, right? Exactly how do you kind of go about setting up your mesh, and what goes into determining how dense it is? Is it kind of like wellbore trajectory? Is it just basically the length of the drill string? Is it kind of contact points, for example, stabilizers that are around it where the grid gets more dense? Just wondering if you kind of comment on that.
Yeah, I mean, yeah. So to my own knowledge, there's nothing I can do about the computational time. I have one procedure, which is what I'm showing you now, how I calculate it. And I think the easier way to reduce that time is to remove some components that you want to assume. So is to store some results and remove those results of those components, those components out of the process, so that you're not labeling, you're only labeling what is new that's coming into the whole. It's something I think is possible, but I haven't done that yet. So what I've done is I've created, because I mean, those for loops are very crazy. So what I've done is to increase, so how do I explain? This is the wellbore and this is the pipe. So the pipe keeps entering the wellbore like that. And that means as it's entering, the members are increasing, right? So one way you can, and the reason why it's difficult for you to assume that because I've calculated the stiffness in this place, I can just assume them and then just calculate this. That would have been the shortcut. But this well part is changing, right? So you calculated the forces here, but by the time you go deep inside, the well part has changed. You might be turning. So what do you do at that point? So that means those forces you calculated initially at this point is different when you go on deeper into the hole. So right now, I think if you can go into quantum computing and get some faster computers, that can help to facilitate the speed of the simulation.
Okay, thank you.
Yeah, kind of along that line, I'm wondering. I mean, when we've looked at stiff string modeling, we've done some used commercial stiff string models that are available, and it seems, number one, if you don't have anything but 90-foot surveys, so if you don't have higher resolution survey data, you don't get enough detail in the wellbore to really have much of an effect. That's like a rule number one. Seems to be I need 3-foot spacing on survey data or better. The other would be, and I think many people have said this as well, is you don't tend to see stiff string effects in the drill pipe. Much more so in the BHA. Now I'll back up on the buckling part of it, but let's just talk about the extra contact force. Would it be possible to run the stiff string effect, or run the stiff string data on, and then come back and say, the extra side force is less than 10% error. If in other words, if the contact forces were less than 10% of the soft string values that existed already, might we even care? In other words, you just say, hey, I can, in this application, I can run a soft string, and in this other applications when I need stiff. I don't know, just kind of going down that.
Well, it depends on your risk tolerance, because you saw the importance of torque and drag there. If you are going to go beyond if you risk going beyond the buckling limit, that means you're going to trip up and trip in, trip out and trip in. Well, you know the dollars implication of that. So it depends on your risk tolerance. And then if you have offset wells where you've done some post analysis, right, and you've done the stiff string modeling, and you pretty much have an idea of what friction factor you should be using, then you can play around with that. But like I said, the numbers don't lie. So if you go beyond the tensile and the buckling limit, then you're bound to face problem.
Yep. Well, and in fact, actually, we had a well several years ago that soft string model did not pick up the difference between pick up and slack off. There was quite a bit of asymmetry between the neutral value and the pickup and the slack off, which we attributed to stiff string. We did not have high resolution data in that initial case, and we had to, based on some assumptions that we made, we had to add a simulated high resolution survey data, which had a spiral in it. It was borehole spiraling. We had evidence for that, but we added that and found that then matched, or we could, without too much additional hand waving, so to speak, we could make it match very well. But it was one of those, that was one of those lessons of hey, I need high resolution survey data if I'm going to do this work. And anyway, for what it's worth. But
yeah.
Yeah,
go
so
ahead,
just wondering if there's any other questions. I have maybe one more, but I'd like to open it up. Okay, I guess one additional question. This might be kind of way out there. Is is there any kind of relationship between the kind of fluid or mud viscosity to calculation of this torque and drag and use it in this model?
Yes. So if you look at the one of the equations that, sorry, just one of the equations in the stiff string model, we actually consider viscosity at some point.
Oh, okay, great.
Yeah, I'm trying to find it. It's not there right now, but yeah, we consider it in the stiff string modeling.
Okay, and is that a big impact, or is it kind of small?
Well, it's I mean, depending on so at the end of the day, there's a force acting in the axial direction, right? And that drilling mud is part of the force. So that drilling mud density and everything that affects the drilling mud is part of that force that's acting in the axial direction. So that can even become a load in the drill string, right? So somehow viscosity would affect, if viscosity affects the drilling mud, and the drilling mud is part of the forces acting on the drill string or acting in that whole setup, then yes, it has an impact.
Yeah, I can reinforce that as well. Again, in these super long ERD wells that we drill, and actually just showed up again in some of our land US, which are starting to get pretty long wells. There is a shear force on the outside that is significant. So that if you measure, like in torque and drag, James, if you measure the hook load with pumps, let's say off, but pumps at a low pump rate, and then you bring them up to full pump rate, you can have multi-thousands of pounds difference in hook load.
Wow.
And normally one doesn't care much if it's if it's big hole like 12 1/4 and 5 1/2 inch drill pipe or something, but if you got 5 1/2 or 5 7/8 inch drill pipe in an 8 1/2 inch hole, and you got 20,000 feet of that, those are big numbers. Those are really big numbers.
Wow.
And
okay. Yeah, it sounds like a big delta. Okay.
Yeah, it is. It is. I'm looking at some data. Literally, I'm looking at some data that's pulled up on another screen this morning on a land US well that shows this effect. So,
wow, great. Okay. Yep.
Cool. All right, where do we go from here, Darlington? What's next? What are you going to do for us, man?
Well, I mean, if you can attend the robotics competition, then you can see what we have gone from here.
Excellent. Excellent.
All right. Thank you.
All right. So thank you for that, Darlington. And again, as always, wonderful conversation. So I think with that, I'll go ahead and stop recording.